Hello, today we'll present our final project for Data Science 1, which is a model predicting the Yelp star review for restaurants. I'm Eliane, I'm a senior at Harvard College.
And I'm Oleg, a junior at the college. First, I'll start with the problem statement, motivation, then I'll move to the processing, and Eliane will talk about the model, and I'll finish with some visuals and conclusions. So our goal is to predict the star reviews of Yelp restaurants, and our motivation is to help users and consumers to make more informed decisions. So initially, we had three different databases. We decided to go with the business database that also includes the ratings to build our prediction model. So most of the columns we actually initially ended up dropping because they're not relevant to our model. And we also had to unroll the attributes because that's where most of our predictors are. Then we used different encodings to encode the attributes from one hot, ordinal, and boolean, and we also imputed the missing values. Or we also dropped some of the columns altogether if there were too many missing values.
So after all this processing, we are left with 50 predictors. And as you can see, these predictors showcase some correlation both internally and with the response variable. So we cleaned out the collinearity by dropping some predictors and we pair plotted. And as you can see, you cannot see clear correlation and clear relationship between the predictors and the response. So essentially, we see little to none direct correlation between the predictors and the response variable. And this makes sense, given that most likely the main causal predictor to the rating is the actual quality of the food. So given our weak predictors and low correlation, we started testing different classification and regression tree models. When we started out, we saw star as a categorical variable. We perceived the decision of giving a restaurant 5-star, 4-star, 3-star more of a categorization of how your experience was attending that specific location, rather than a grade scaled from 0 to 5. For basic comparison, we went with a single tree and used cross-validation for the best hyperparameters. Then we used grid search to optimize the hyperparameters for the random forest and the XGBoost model. Unsurprisingly, XGBoost, which is a good model to use when we have weak predictors, was the most accurate out of the three. That being said, we weren't satisfied with the classification model's accuracy, so we moved to implementing regression models, which would also help with diminishing the effects of class imbalances. Again, we utilized grid search to find the best hyperparameters, but we also used regularization parameters, which operate by applying an elastic net style regulation, shifting our total cost. The results were a little better, and XGBoost seemed to be our winner model. So up until now, we got our business data, processed it, applied the winning tuned XGBoost regression model, and now we'll move to evaluating how this model actually does. The first thing that is important to note is the training details. It took us about 40 minutes to run this model on a standard Google Colab CPU. We use 500 trees, and for the learning rate, we use the default, which is 0.3.
Observing the distribution of our results, we noticed that it's different from given distribution of the data. Then we tried to use the different methods such as gamma and tweedy for the objective for XGBoost, but then it turned out that the squared error was actually the most optimal.
So not to go too much in depth, because you can always check out our notebook, but generally speaking, you use normal distribution for data that is symmetrically distributed around the mean, including negative values. You opt for the gamma distribution when dealing with right skewed data that is strictly positive and where the variance increases with the mean. You choose Tweedy distribution for mixed data types, especially those with a significant proportion of zeros and a continuous component. So given the appearance of our data, we thought maybe we should check these two out. But they ended up making our model worse, so we ended up scrapping that.
And we believe the distribution of our results might be due to the central limit theorem when using multiple weak predictors. Here we can look underneath the hood, observing one of the decision trees in that sample, starting from business parking decision added root, going down through leaves, and we can see the values that this particular tree, how much it affected the model. And using SHAP to observe how different features impacted the model overall. We can see that the alcohol bar actually increases the ratings. As the restaurants get more expensive, the ratings also slightly increases, and also as the noise level increases, the ratings actually decrease. So as a conclusion, our final model has MSE about 0.5. That adds up being, we take a root, about 0.7 mean difference between our predictive and the actual true values as observed on the test data. We believe this is acceptable because there are some unobserved variables such as food quality and service quality, and also the Yelp's rounding of the variable. And in the future, we would like to fix this rounding issue of Yelp by calculating our own review ratings using the user database, and also explore causality from the text.
Thank you for listening to our presentation, and thank you for a great semester.